This video is on pH. If you've ever done a lab before with acids and bases, I'm sure you have tested the pH of different substances using something called litmus paper. I'm sure you've taken little tiny strips of paper and dipped it in each substance, and then the paper would either turn red or blue, and that would tell you if it's an acid or base. So indeed there you were testing for pH. Litmus paper is one indicator to test for pH. You can use other indicators as well, such as a pH probe, and that can give you a digital reading. pH stands for the power of hydrogen, or the potential of hydrogen. So that is what the little p, power or potential of hydrogen. So the definition of pH, it measures the concentration of your hydronium ions in aqueous solutions. Recall that these hydronium ions come from acids. So if we have these brackets here, that stands for concentration. So whatever we have inside, this says the concentration of H3O plus. And this concentration is usually in terms of mole per liter, or big M, which stands for molarity. So we have that. We have the concentration of our OH minus, our hydroxide ions. And just numbers to know for pH, the scale goes from 0 to 14. If you have a pH of less than 7, that is an acid. In an acid, your hydronium concentration will be greater than your hydroxide concentration. And that is because your acids are derived from your H3Os and your bases are derived from your OH minuses. So you need more H3Os in an acidic solution. If your pH is greater than 7, that is when you have something basic or alkaline, and your hydronium ion concentration would be less than your hydroxide concentration. And if you are right in the middle, if you are at 7, that is neutral, and that's when your concentrations will be the same. An example of something neutral would be water. We have seen these numbers before. Our blood pH is very sensitive and has to be in this very tight range. If your pH drops below 7.35, you get acidosis, and if it's above 7.45, it's alkalosis. And both of these are very dangerous conditions and can be life-threatening. You can have kidney disease, you can get strokes, you can have depression of the respiratory center by drugs, narcotics, and poisons. A bunch of different things can happen here. Here are just some examples of body fluids and their normal pH ranges. You can see some have a wider range, like your urine is anywhere from 5 to 8, so it can be acidic or it can be slightly basic. And then some have a tighter range, like your blood. The range here is only 0.1. So here is an important constant. It's called Kw. It's the autoionization of water. So water is the solvent in a lot of different things. It's the solvent in your cells. It's a solvent outside your cells, in blood, many other body fluids. Water is the solvent in. So if you have pure water, those water molecules are still interacting with each other. And what happens when they interact with each other? Here we have two water molecules. One is an acid, one is a base. We know water is amphoteric. And your acid will donate its H to the base. And your acid turns to your conjugate base. And your base turns to your conjugate acid. So look what we produced when this autoionization happened. We got our hydroxide ion and we got our hydronium ion. Now these two will be in the same concentrations, and that's where we get our Kw constant from, which you will see on the next page. So if we have pure water, your H3O concentration is 1.0 times 10 to the negative 7th. Your OH concentration will be equal to that. So 1.0 times 10 to the negative 7th. Your water, your ion product constant for water, you multiply those two ion concentrations. So if you would multiply 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, you get your constant of 1.0 times 10 to the negative 14th. That is something you want to have memorized. We will use that constant in order to calculate these two different concentrations here for hydronium and hydroxide. This is a nice table showing the relationship between pH and the different concentrations. So on the left-hand side here, you have all your pHs. Again, your halfway point is 7. Any pH below 7 is acidic, and anything above is basic. The further you get from 7, the more acidic or basic something is. Your H3O plus concentration of something acidic will be bigger than 1 times 10 to the negative 7th. So all of these. And if you are smaller than 1 times 10 to the negative 7th, you are basic. Now notice I'm saying smaller for the higher exponents. And let me explain that a little bit here. If I have this number right here, 1 times 10 to the negative first, if we get that out of scientific notation, that's just 0.1. If I take 1 times 10 to the negative 13th out of scientific notation, that's 0.000. I believe that's the amount of zeros you would need there. So while the 13 is a larger number than the 1, they are negative. So this number is bigger than this number. So I just wanted to clear up any confusion you might have there. And on the opposite end of the spectrum, your OH concentration, if it is acidic, your OH concentration will be very small. So if you have a pH of 0, super acidic, look how small your OH is. And if you're basic, you'll have a big OH. In any case, if you compare the two straight across, when you multiply them, it's going to equal your Kw. It's going to equal 1 times 10 to the negative 14th power. And base 10, especially when you have a 1 as your base here, it's very convenient because you can just add the exponents and you'll always get to negative 14. So if you look at negative 4, negative 10, or negative 7, or negative 5, negative 9, they always equal negative 14th. And that's because these are a 1. So you just multiply your 1 times 1. You can, of course, use your calculator to do that as well. So here's a practice problem that says, what is the hydroxide ion concentration? So I'm just going to draw what that is. For an aqueous solution with the hydronium ion concentration of 1 times 10 to the negative third. So if we're looking for concentrations, we know our formula, our Kw, equals the two of them multiplied by each other. So if I just plug in what I know here, I know my H3O. And I don't know my OH. So using basic algebra here, I'm just going to divide both sides by 1.0 times 10 to the negative third. And I will get my answer of 1.0 times 10 to the negative 11th. And you can use your calculator for that, or if you're good, you can divide your bases. So 1 divided by 1 is 1, and then subtract your exponents. So negative 14 minus a minus 3 is negative 11. What is the hydronium ion concentration? For an aqueous solution with a hydroxide ion concentration of 1 times 10 to the negative 10th. So the same idea here, we're just looking for the other one now, but we still use our same formula. They're always going to multiply to 1 times 10 to the negative 14th. So we're going to plug in what we know. And we're going to divide both sides by 1.0 times 10 to the negative 10th. And we get our hydronium concentration of 1.0 times 10 to the negative 4. Is this an acid or a base? Bonus question. Well, if my H3O is negative 4, 1 times 10 to the negative 4th, and my OH is 1 times 10 to the negative 10th, which is bigger? This one would be bigger, right? Times 10 to the negative 4th is bigger than times 10 to the negative 10th. So my H3O is bigger, which means it's more acidic. So this would be an acid. Now, what if we already have one of the concentrations and we want the pH? So there is a formula for this that you will want to memorize, and it is pH equals the negative logarithm, that is a key on your calculator, of the hydronium concentration. So in your calculator, you can just press negative, look for the log button, and then type in your concentration. So if we're looking at pure water, for example, and we know the hydronium concentration is 1.0 times 10 to the negative 7th, which we've said before, and we type that in the calculator, your answer is 7. And the pH of water is 7, so that makes sense. You can maybe see what's happening here. Again, because your base is a 1, what happens is your exponent becomes your answer, and it turns positive because this negative cancels. So really nice when your base is a 1. So what you can infer from this is that your pH plus your pOH is equal to 14. Look at the similarity between your H3O plus times your OH minus. Notice how the numbers are similar here. You get back to that 14 number. pOH, you can find the same way using the negative log, except instead of the H3O, it's the OH minus. But still negative log. So as your H3O is increasing, your pH decreases, right? pH is below 7 for acidity, and as H3O increases, it becomes more acidic. So just looking at these two numbers here for hydronium concentration, we could plug it into our formula and see, okay, the pH is 6, the pH is 4. Logarithms, if you remember from math class, is a 10-fold change. It's base 10. So while it looks like it's only 2 units stronger, it's actually 100 times different in concentration. Every 1 unit is a factor of 10. So if you have a pH of 5 and 6, that's 10 times stronger, or higher concentration. If you have a pH of 1 and 10, that's 10 to the 10th times stronger. What is the pH of a solution with a hydronium ion concentration of 1 times 10 to the negative 9th? Is this solution acidic, neutral, or basic? So we have our H3O concentration, and we're looking for pH. So if I'm looking for pH, I'm going to write down my pH formula. These should be brackets. And I'm going to plug in what I know. my pH here would be 9. If my pH is above 7, which it is, that means it is a base. Bonus question, what is my pOH? Remember, they add up to 14. So if my pH is 9, my pOH is 5. And the last problem here, what is the hydronium ion concentration of a sample of stomach acid with a pH of 2? So here we're looking for the H3O and we're given the pH. So we do not have a formula for this as of now, but I'm going to show you what it is. So this formula is great if we know the H3O+, but we don't know that here. We're searching for that. So through algebra, we can divide both sides by -1 to get rid of that negative. So now we have negative pH equals the log of the H3O+. And to undo a log, or to inverse a log, you raise both sides 10 to the power of both sides. So that's just your algebra there. So 10 to the negative pH equals your H3O+. And you don't need to know the algebra. What you need to be familiar with is this equation. So we have the pH of 2. So to solve this, we're going to do 10 to the negative 2. And that'll give us our answer of 1 times 10 to the negative 2 molar. That is our answer. That is our hydronium ion concentration.